have enough buoyancy to effectively lift the hot air balloon. So you also don't really want it all that windy because you don't want to get tore up. You know, when you land, you kind of like it to be a nice, easy landing, not. All right. So this is full of a mole of this gas. Now you've probably all played with beach balls, right? So there is not any difference really between this beach volleyball and anybody else's other than it's got this cute little thing on here that says a mole. All right, so we're going to pass it around and you're going to notice something. Now, just for the sake of having fun, we're going to blow up another balloon. And I blew that one up with my breath. I'm going to use this tank. Now this is the beginning of an LLE. All right? So number one, we're going to do some comparisons. We're going to compare this balloon to the one I blow up here. The only difference is it came out of the same package. This one's yellow, and if it doesn't have a hole in it, we'll keep using it. And that one's green. I'm going to try and blow it up to about the same volume, so you've got a fairly accurate comparison. Oops. You agree? Is it weird yet? If that's not weird, this probably will be. Let's try and avoid popping, shall we? Yeah. All right. There you go. Notice any differences yet? Okay. All right. So what I want you to do is observe these the differences and try and get an understanding of perhaps what the molecular difference is between air and this gas. All right? Now, I don't really want to tell you the identity of the gas. I probably will, but that's part of this LLE. We're going to try and determine, based on our observations, what are the properties of this gas? Okay? So, LLE number 3, it is properties of a gas. Now, you know a lot of things about a gas. You know P1V1 over T1 equals P2V2 over T2. There's also this other equation called the ideal gas law, and that's P, which is pressure, times volume, equals N, which is the number of moles of the gas, times R, which is a constant called the molar gas law constant, times temperature. And we usually use temperature in Kelvin for that. All right? So what this says is the pressure times the volume is the number of moles of a gas, and for any defined system, that's a constant. The molar gas law constant, self-defined constant, and the temperature. All right? What's nice about this is we can determine the number of moles in a system simply by measuring its temperature, volume, and pressure of any gas. That makes it kind of unique. All right. I'm going to do, I was going to do one other thing. I don't know if I can. I'm going to skip this demonstration. I think. All of a sudden you guys are sad.
Was this the whole LLE?
That's not all of it, because I'm going to ask you to do another observation. So what I want you to do is try and get a handle on what are the properties of this gas, okay, in terms of its density. So we know we have some experiential knowledge on the density of air, how it's affected. We have some knowledge on the density of other gases, like helium, right? One of the interesting properties of carbon dioxide is that it's a gas, right? Yeah. What is it used for? If we freeze it, it's dry ice, but then it's no longer a gas. What do we use the properties of carbon dioxide as a gas for? Do you know where you'd find it?
The air?
Yeah, we find it in the air. Where else do we find it? Turns out we fill fire extinguishers with it. Why would we fill a fire extinguisher with carbon dioxide?
So then
3 words.
To put out the fire?
Works. Because, why? It doesn't burn. Now, helium doesn't burn. Why not use helium?
Because when you shoot out, it just goes straight up.
Aha, because your helium fire extinguisher, things tend to burn, what? From the bottom. And then as that heat expands the air, the fire tends to raise. If we were to try and put helium on the fire, it wouldn't get there. It'd be a difficult situation. So notice carbon dioxide, C, 12 grams per mole, O, 16, and 2 of them, that's 32. The total is what? 44 grams per mole. Oxygen, 32. Nitrogen, 28. So air is about 30. What is carbon dioxide with respect to air?
More dense.
It's more dense. That's what gives it one of its unique firefighting properties, right? Because it sinks and smothers a fire. Take at home, as part of this LLE, do this demonstration. Take a candle and put it like one of these little tea light candles, right? Or a birthday candle. Okay? Or if you can't afford it, a match. All right? Put it in a tall glass. Now, take on top of the tall glass, place another thing, like a non-burnable plate or something like that. Have some distance between the fire and the candle and the thing that you top the glass with, okay? And watch the candle as what's ultimately going to happen. We all know this. If it's sealed on the top, what's going to happen?
It'll go out.
Yeah, it's going to go out. It's going to get smothered. But pay close attention to the flame. What happens to the flame? Now, don't disturb this thing. Leave it sit on the table and close the top and watch it. And do it a couple of times.
Doesn't it start
Okay?
flickering?
So just watch it and have a hypothesis on the front end of what's going to happen to the candle. Okay? And then watch it and see if your observations match your hypothesis as usual. All right.
So our LLE is the candle?
That's part of it. The other part of it is coming up right now. So, density. What would you expect this gas's density to be compared to that of air?
More dense.
So that is a question on this LLE as well. Okay, so what's the density of this gas compared to the density of air? I will tell you that this is an inert gas. It's not like hydrogen. Okay? It's not a reactive gas. And I'll show you, I think this might be interesting.
Balloon animal.
I'll show you, and no, I won't be asking you to blow this up.
Thank you.
You are very welcome.
I wouldn't mind blowing the other balloon, but
Notice
that one-
this is a lot easier.
Is this the type of air they use for balloon animals?
Nope.
Nope.
Way too expensive for that. So, here is the final observation that you need to make for your LLE. What I'm going to do is I'm going to take this. It's not very much gas in there. But I'm going to take this anyway and try it out. Now I'm going to just tie this one. Come on. That much. This is kind of interesting thing. Is that weird? Kind of Wile E. Coyote bothers you a little bit, you know? Why do I say kind of Wile E. Coyote bothers you? Why do we laugh at Wile E. Coyote? Because the laws of physics, even though he knows them, he thinks he knows them anyway, they change for him. And that really ticks him off. The laws of nature just don't apply in his world. Well, he thinks they should, but they never work out right. So, I filled this balloon up. I told you it's a chemically inert gas. I'm going to do a little demonstration for you. Are we ready? What's this mean? Okay.
Very white.
Hmm?
Very white.
Alright. Now, the hypothesis here is, what do you think is going to happen? We know some stuff about this gas. Have you ever seen anybody breathe helium? That's an inert gas.
Yeah, they start sounding like a tick one.
That seems to be your hypothesis. If it's everybody's hypothesis, write it down. What's going to happen when Dr. Nye breathes that gas? All right. Are we ready? Time for a little oxygen. Why don't I have to do that when I breathe helium?
Because they'll come out for you.
Yeah. So, yeah, I decided to get some air, so I did this. And why did I do that? I don't ever do that after I breathe helium and talk like a chipmunk. So, put that in your little observational notes as well. How was your hypothesis?
Opposite.
Now the question is, why?
It's more dense.
But why? So don't answer this now. Try and answer it and do some research. You know, in this day and age, what do we get to do? We JFGI everything, right? Just freaking Google it, right? We, what is it? Now, you have to realize that not all the answers on Google are posted by geniuses. So you also have to be a little scientifically minded when you read it and try and deduce whether or not these people that wrote this answer have an accurate handle on what's happening. But it's a good place to start. So, think about it. Think about kinetic energy of molecules. Think about how much space they have to move to take up a volume. Think about what's happening. What's happening on the wall of this balloon? Most of the answers to these questions can be found in your textbook, by the way. Go figure. But do think about that. So I'm going to do this one more time, or, you know, if somebody is absolutely...
You should do a ransom call. Call my mom, tell me
That would be really fun, actually. Your mom would be like,